So the first thing I wanted to do today is I want to kind of talk to y'all about some housekeeping stuff, what's coming up, like due dates and stuff like that. So tomorrow, the 18-week session and the 16-week can have a due date. And the 16-week session, you guys are going to turn in everything from the frame of reference discussion or the your welcome discussion and your handbook acknowledgement form all the way to your frame of reference discussion. Okay, so if you're counting the things that are due, you have 8 items due, and that's including your handbook thing, your handbook acknowledgement form. And that also includes a test, okay? So you need to make sure that you take that test. That's your math and physics test. I'm going to just write it like that. Okay, 18-week kids, you guys have, let's see how many things you guys have 4 things due, and one of those is a test as well. And that's your 1D motion test. So I'm just gonna write it like that. Okay. So these are both due tomorrow. Now, 16-week kids, there is a review that I've recorded for this math and physics test. I highly recommend you looking at it. You can find it in the user link section, or you can find it in the the course resources newsletter for math and physics. 18-week kids, there is a review where I did everything but the graphs last week for this test. So there's a review for that as well. And then if I have time tonight, I'm going to kind of talk quickly about the graphs. And 18-week kids, your test actually has a short answer section. So make sure when you do that, you're showing your work because you get points for showing your work. So that's really important. So that's really what I wanted, kind of the housekeeping stuff I wanted to talk about with you. Looks like the 6th of September, you guys don't have any tests due either group, so you guys kind of have a week reprieve, and then you'll probably have a test the next week. So what I'm going to do is I'm going to go into the horizontal projectiles. I've got my slate. It's kind of going in and out, but I'm going to try my best. And if it doesn't work, I've got the review recorded, but I do kind of prefer to do it live. I think it's more helpful to you guys. So these are our formulas for projectiles. And the reason I really want to focus on projectiles today is because projectiles are usually one of the most difficult things that we study in physics. And so I really wanted to kind of focus on that. If you look on the website under user links, I have some extra projectile practice problems uploaded there, horizontal and vertical or angled, and I have the keys to those as well, so you guys can see those in case you want some extra practice problems. And then I also, if you go to the course resource newsletter for this section, I have some more videos of me working through these problems. So hopefully that will be helpful to you. Now, these formulas, I don't expect you to memorize these formulas. In fact, I don't memorize these formulas either. I've got enough on my brain without memorizing a formula. So, but these are all the formulas that you would need for a horizontal projectile. The big thing that I really want to stress is that I'm going to pick a color. It's not black. This is for horizontal velocity only, and this is huge. Okay, I see a lot of you guys solving problems that involve acceleration using this formula. You can only use this formula if you have a constant velocity. Okay. If you don't have a constant velocity, you can't use this formula. Okay, it's not going to work. So in the horizontal direction, that's weird. In the horizontal direction, we have no acceleration, right? Because acceleration due to gravity is up and down. And so we can use this formula to get our Vx. But you can only use it for horizontal velocity. You cannot use it to find final y velocity, anything that involves acceleration, you cannot use it. And then also for these horizontal projectile problems, you always want to solve for time first. If you don't solve for time first, you won't be able to do anything else. So even if the problem doesn't ask you for time, solve for time and then solve for whatever else it's asking you for. So that's really the most important part of that slide, or those two things are the most important part. So let's kind of work through this horizontal projectile problem. Okay, so we have a stone thrown horizontally at a speed of 5 meters per second from the top of a cliff that is 78.4 meters high. Okay, so and then it says how long does it take? So luckily, how long is a time? And so it's asking us for the, what the first thing we want to solve for anyway. So whenever I do one of these problems, the first thing I do is I draw it out. Okay, so I'm going to draw my vectors. Remember, at the beginning of this unit, we talked about resolving vectors. And so that's kind of what I'm doing here. I'm going ahead and I'm breaking it into components. So this is my, this is going to be my Vx, right, which is what this is. This is going to be my Vfy. And the reason is because my VIY, my initial y velocity, is just 0 because my stone was thrown horizontally. So we don't have an initial y velocity. Okay, so we can even write that like this. Okay, my Vx is equal to 5 meters per second. Okay, so I know those two things. I know my initial height is, sorry, I'm trying to do my little hack to get my slate to work. My initial height is 78.4 meters, and my final height is 0. Okay, so this right here, right here is what we would call our vector velocity. So I'm just going to call it V. And then I can draw my height in here if I want to. But I just like to draw a diagram of what's going on. I think it makes it helpful for me anyway. And so if you look at the formulas that you were given on the previous slide, when we want to find the time, there's only two formulas that have t in them that we can use. And we have to use this one because, get this to work. We have to use this formula because the other one has your final y velocity, and we don't know that yet. So there'd be like two things that we don't know. This can be hi too. I just kind of interchange those. Okay, so here's my formula. Now I'm going to go ahead and I'm going to plug my stuff in. And I'm going to keep my units here. And the reason I'm keeping my units is because I don't want to accidentally add things together that don't belong together. My initial y velocity is 0. Now, since my initial y velocity is 0, I'm just going to write 0 because that's going to cancel out anyway in a second. My g, remember, is that value that you have to memorize. Okay. So I'm going to go ahead. I'm going to cross out that. I'm going to take this and I'm going to move it to the other side. Now, because I've been doing these so long, I know that 1/2 times 9.8 is 4.9. But if you don't, you can do that math. But I'm going to do negative 4.9 meters per second squared. And I'm going to just move that to the other side. Since it's a negative, I'm going to add it. Okay, so then I'm going to have 4.9 meters per second squared t squared equals 78.4 meters. Okay, now that I have this, I'm going to go ahead and I'm going to divide both sides by this 4.9. Okay, so then I'm going to get, I'm going to draw it over here, just because it won't let me draw any lower on the screen. I'm going to do t squared equals 78.4 divided by 4.9 is 16. These two ends cross out. So I'm going to have t squared equals 16 seconds squared. Now, a lot of students stop here. They don't keep their units in, and they just time 16 seconds. But that's not true, right? This is t squared. So we have to go ahead and we have to square this. Okay, so we get t is 4 seconds. Okay, and we'll need this in our next step. Okay, but that's how you get the time. Okay, so let's go to the next slide and let's try and do the next step of this problem. Okay. So we still have everything that we knew from before. Okay, but this time it wants to know how far from the base of the cliff does the stone hit the ground. So it wants our d, or our horizontal distance. Okay. Now, since it wants something in the horizontal direction, we can use our Vx to find this. Okay. And since we can use our Vx, we can actually use this formula because we're in the horizontal direction. If we weren't in the horizontal direction, we could not use this formula. That is crucial. Okay. That's the only reason I'm using this formula, because I'm looking for something in the horizontal direction. Okay. Otherwise, I couldn't use it. Okay, because the y direction has an acceleration. So instead of doing algebra, I'm going to go ahead and I'm going to put this in the triangle. I'm looking for d, so I'm going to cross d out, and I'm going to have d equals Vx times t. Okay, so I'm going to have my 5 meters per second times 4 seconds. Okay, my seconds will cross out, and I'll get a d of 20 meters. Okay, and that's how we find our or how far from the base of the cliff. And that, remember, we can only use that formula because it's in the x direction. Okay, so let's see what they want in part C. In part C, it looks like they want the horizontal and vertical components of the stone's velocity just before it hits the ground. Okay, so we've got this, this, and this. It wants our Vx final and our Vi, our final y velocity. Now, Vx is the same the whole time, right? It's a constant velocity. Okay, there's no acceleration in the x direction. So our final x velocity is the same as our initial x velocity. It's just 5 meters per second. Okay, we don't have to do any math to find that one. Okay, the other thing we need is our final y velocity. And that one does change. Okay, and I'm going to use this formula because I've already found my time, remember? I'm going to put my time of 4 seconds here. And so I'm going to do okay, so I'm going to do this. So I'm looking for that final velocity. My initial y velocity is just 0. And my g is that negative 9.8 that you have to memorize. And my time is that 4 seconds. This second and this second will cross out. So then we'll have basically negative 9.8 meters per second times 4. Okay, and that's going to give us 39.2 meters per second. And you see this is a velocity, right? And we've got a direction here, right? A negative. That means we're going down. Okay, so it means that velocity is, headed in a down direction, which is, what we expected. And so there's nothing weird about that number or anything like that. It's, it's totally fine. But that's where that negative comes from. Okay, so now let's do part D. Okay, part D wants that impact velocity. That's what they're calling it. I call it the vector velocity, but you can, a lot of people call it the impact velocity. Okay, so they're looking for theta, and they're looking for v. So if we were to draw our scenario, okay, we're looking for this guy and this angle. Okay, these are the two things we're looking for. Okay, and we're going to use our, to find that, we're going to use our Vx and our Vfy. Because our VIY was 0. Okay, so to do this, we are, this is a right triangle. So we're going to use, let me draw what we know. Vfy is negative 39.2 meters per second, right? We got that in part C. And Vx is 5 meters per second. Okay, and so to do this, since it's a right triangle, I'm going to use the Pythagorean theorem. This a squared plus b squared equals c squared. Okay, so I'm going to have negative 39.2 meters per second squared plus 5 meters per second squared equals c squared. Now, if you want to put this in your triangle or in your calculator all at once, here's what I would do. I would put an extra parentheses here. You may not need it, but I'd rather be safe than sorry. Okay. So then you end up getting 1536.64 meters squared seconds squared. Don't worry, we'll get rid of those. I know that's weird. And 25 meters squared seconds squared equals c squared. Okay, and then we are going to take the square root of that, and I actually just put this in my calculator once, so I don't have what that number was. Let me just, I'm going to get it for you real quick. 1561. We've got that meter squared second squared, but remember that square root's going to take care of that. Equals c squared. It's not going to let me write any lower than this, so I'm just going to kind of, that's odd, go over here, and I'm going to get 39.5 meters per second. And if I look at my triangle, that makes sense, right? These weren't drawn to scale, but because it's the hypotenuse, I know it's going to be a little longer than whatever the longer value of these two are. And so our VFY was 39.2. And so 39.5 is a little bit longer than that. So that's, that's okay to me. That checks out. And then to get my theta, or my angle, I'm going to do the inverse tan of my VFY over VX. Okay. Now, just kind of a hint here. I've tried to do inverse tan on my phone, and my phone is like default in radians. And so I highly recommend. Okay, let's see if that comes back. I highly recommend if you're gonna do your math on your phone. I would use a regular calculator, but if you're gonna do the math on your phone, I highly recommend that, or like I would download like a graphing calculator app or a scientific calculator app or something like that, and do that. Otherwise, you're going to get something, you might not get the right answer. And a hint, if you're, in order to figure out if your calculator's in radians, if you get like a really small number when you take the inverse tan, or when you're doing, then like a decimal, then you know it's in radians. Okay, so I'm gonna get 82.73. And the reason it's negative is because when we do these, they're based on like if this was our coordinate plane or whatever, and since our angle is down here, it's saying it's down from the x. So that's why we get that negative 82. So that that doesn't freak me out. I'm okay with that. Okay, so now let's do an angle projectile problem. I personally think the angle projectile problems are a little more difficult, but some people don't. The problem is there's like one more extra step usually, and so that's why I don't like them. So when we want to solve for these, you always want to solve. You're going to use the same formulas you used before. You're not going to need the Pythagorean theorem. Still, you can only use Vx if you're talking about your horizontal velocity, but you will need to solve for the horizontal and the vertical component of your velocity. And so to do that, you have to use this formula. and you have to do that part first. So even if they don't ask you to do that part first, you have to. So let's look at this problem. So in this one, we have a ball launched at so this one we have a ball launched at 4.5 meters per second at 66 degrees above the horizontal. So the first thing I want to do with one of these problems is I'm going to draw it out. Okay, so this is our vector velocity here. We're just going to mainly work with this first half, this first triangle, and so our final y velocity is actually going to be 0 because like at the top it stops for a second before it comes back down. If we decide to work with this half, then we'll just call that our initial y velocity. And then this is our this bottom is our Vx. Okay, so what do we have? We have our they've given us our vector velocity, which is 4.5. And so I'm just going to make that like V plane. And then we have our theta is 66 degrees. We have our VFY is 0. And then they want us to find the x and y components of that initial velocity. So they want us to find Vx, and they want us to find VIY. So to find the Vx, I'm just going to do that AX equals A cosine theta, like when we were resolving vectors at the, this is kind of what you do at like the beginning of the 2D motion unit. This is the first thing they teach you. And so our A is going to be that 4.5. And then our cosine of 66. Okay, so I'm going to get 1.83. Okay, so that's going to be my Vx. Okay, and then I'm going to solve for my AY, which is going to be a sine theta. So I'm going to still have that 4.5, but I'm going to take the sine instead of the cosine this time. Okay, so what I was saying is that for a horizontal projectile problem, you want to start, the first thing you want to do is solve for time. But for an angle projectile problem, you have to solve for those two components, but then you still want to solve for time next, which is, like your first real thing or whatever. So luckily they're asking us for this, and usually they ask you for time pretty early. But if they don't ask you for time, go ahead and solve for that first, because you'll get stuck and you won't be able to really go anywhere else without that. So I'm just going to write on the left what I know. I know my VFY is 0. I know my Vx is 1.83. I know my VIY is 4.1. And then I know like my vector velocity, so I'm just going to call that like v plane, or v without anything else, is 4.5 meters per second. So I want the time. So if you look at those formulas I showed you, and you don't have to memorize those formulas, write them down and have them with you when you take the quiz or the test. Don't try and memorize them. It's not worth it. It's just a waste of your time to try and memorize those. So I've got them written down for me because I knew that I would need them. And so I'm going to use this formula because the other formula that has time in it has like height in it, and I don't know any heights or anything. I haven't like gotten that far. So this is the best formula for me right now. Okay, and then I'm just going to fill in what I know and solve for time. And I'm going to put my units in here. And the reason I do my units is because I don't want to accidentally, add things together that aren't allowed to be added together. They don't have the same units. This 9.8, that's our that's that gravity that you have to memorize, and you get your bang for your buck out of this gravity. So if you memorize it, you're going to use it like all the time. So it's not like you memorize it and then use it like once and it's like, gosh, that was a waste. You'll literally use it like almost all semester. So I'm just going to add this to both sides. I have a help ticket in for getting this slate to work better. And they were like, yeah, we don't really know. So then I'm going to have 9.8 meters per second squared equals 4.1 meters per second. Okay, I'm going to divide both sides by 9.8. And then the meters are going to cross out, and then this 1 second will cross out, and then that second actually ends up being like on the top because it's on the bottom. It's on the bottom of the bottom, if that makes sense. So then my time ends up being, so our time is 42 seconds. Okay. And then it'll probably take you like half that long when you're solving it because you won't have to re-click all the time like I did. And then it wants that maximum height reached by the ball. So we're gonna use that formula. If you remember, I said there was a formula that had a height in it, but we didn't know anything about height yet, so we couldn't really like mess with that. So now that we've got our time, we can actually do something with that height formula. So we can get that height and like actually figure it out. Okay, since our ball is like starting on the ground, right? We go like this, and then we go like this. Our initial height is 0. And then we have that initial y velocity, which was that 4.1 meters per second plus our 1/2 negative 9.8 meters per second squared, and then a time, which is squared. Okay, so then our height is going to equal 4.1 meters per second. And then we're going to have this 1/2 times 9.8. It ends up being like negative 4.9. And so what I did when I put it in my calculator is oh, sorry. There should be a T here. I'm like, what is going on? This does not look right. You're not seeing anything. Thanks for letting me know. Like I said, this software is new, and so sometimes it doesn't do what it's supposed to do. Okay, and there should be a T here, which that was my fault. I forgot to put that in, and so I'm gonna see if I can erase this. So this T is that 0.42 right here. So this should be like 4.1 times 0.42. So then you get 1.72 meters. And then so what I do is I take this this 1/2 times this negative 9.8, and that ends up being 4.9. Like you just like I've done so many of these problems, I just kind of have it memorized that half of 9.8 is 4.9. And then I multiply it by this. And if I'm going to put it in my calculator all at once, which you totally can, that's an acceptable option. I like to put an extra parentheses here around that squared, just so my calculator knows to just square the 0.42 and not this stuff, if that makes sense. So you could like, sometimes I'll even add extra parentheses here just because I like am paranoid of putting something in my calculator and like forgetting a parenthesis and then getting the wrong answer just because I entered it in my calculator wrong. I hate that. I'm like, I did too much work for this to enter it in my calculator wrong. So then you end up getting this 0.86 for this guy, which ends up being 0.86. So that ends up being our maximum height. Okay, so this point up here is 0.86 meters off the ground. And then kind of all your projectile problems kind of like follow from there. An angled, I think, is more difficult than a horizontal. But if you want to see a horizontal problem, I've got one like on the recording, like when I post it, you'll see that at the beginning. When I taught face-to-face physics, we actually only did like two. We only did position time graphs and velocity time graphs, but they actually go one step further in virtual school and they do acceleration time graphs. So we'll kind of talk about those. So a position time graph is just going to have the position on the y-axis and time on the x-axis. And you'll always have time on the x-axis. Time is never on the y-axis. And so when you do that, you know, and you try and find your slope, you know, your slope is your rise over your run or your y over your x, right? So you end up getting, that ends up being your position over your time. Okay, so that is meters per second, which is a velocity. Okay, so the slope of a position time graph is going to give you the velocity. Okay, if they ask you to calculate the displacement in a position time graph, that's pretty easy. Okay, so if they say the displacement from 0 to 5 seconds, then you know you can just look at the top and it's 3 meters. So that's this is the easiest kind of graph, I think. You can't really see anything about acceleration or anything like that in a position time graph. It's just kind of your position, your time, and then your slope is your velocity. So that's all we can really get from one of those. Now, we can go one step farther and we can make a velocity time graph. And so a velocity time graph is it's just like a position time graph, except you've got velocity on the y-axis instead of your your position. So then when you go to calculate your slope, right, your slope is your y over your x. So you end up having meters per second over seconds, which is going to give you a units of, then you're going to get a units of meters per second squared. Okay, so that means the slope of your velocity time graph is an acceleration. Okay, so to get a displacement from this kind of graph, you actually have to calculate the area under the curve. That's what they call it. So that's what these boxes are. So for example, if you wanted your displacement from 0 to 3 seconds, you would calculate the area of this box, and that would be your displacement for there. And since you're this is a rectangle, you know, you would just do the area of a rectangle is just like your length times your width or whatever, or your length times your height, one side times the other side. If you wanted, if you wanted to find the displacement between 3 seconds and 7 seconds, you'd have to do like 1/2, what do they call it, base times height. You'd have to do like 1/2 of this times this, okay, in order to get that area. If they wanted the displacement from 0 to 7, you'd have to take your area, this red area, and add it to this green area. So you'd have to find the red one, you'd have to find the green one, and add them together. Now, we'll see this in the next one. I'm just going to save it for the next one. But they call this the area under the curve, right? So your line, your data point line is like this or whatever. It should be straight. I just can't draw straight. Okay, so that's how you find the displacement on a velocity time graph, and that's what that area under the curve is. Now, let's go to an acceleration time graph, which is the it's not the most tricky, but it's just a little different. So when you have one of these graphs, your acceleration is on the y-axis, and your time is on the x-axis. And then if you want to find, because when you're accelerating, your velocity is constantly changing because you're constantly accelerating or decelerating, speeding up or slowing down. You can't just, without calculus, we can't figure out your instantaneous velocity. And so what they do is you can use the area under the curve to find that velocity. Okay, so with the last one, your area under the curve was your distance or your displacement. In this one, it's your velocity. Okay, and where I think it gets confusing is this makes sense, right? This is your area under the curve, right? Just like we saw before. But then when they have over here, they say the area under the curve, but it's actually, to me, it looks like the area above the curve, if that makes sense. Because your line is here, and it's the area between your line and 0. Okay, so like some students were trying to calculate the area under the curve, and they were like, where do I, when it stops like that, where do I end? Do I do this? Now for this particular problem, if you were to technically calculate the area under the curve, because of the way this triangle works, you would actually probably get the right answer, because they're the same size. But they're not all like this. So that was confusing some students. And so it's really, they say the area under the curve, but maybe a more correct way to say this would be the area between the curve and the 0, or the curve and the x-axis. Okay, so if you're below the x-axis line, then you're actually finding the area above the curve, if that makes sense. So that part is kind of difficult for some people, just because it's kind of weird to think about. And it works the same way. So if you want to find the area of this triangle, this green triangle, you would have to do like the 1/2 base times height. Okay, or if you wanted to do, for this one, the same thing would be like 1/2 base times height. And then for this one, you would probably get a negative number. So then if you had to like add all three together, that would be negative. So it would be taken away from those two. And then if they wanted like the area between like 0 and 7, then you would add this area to this area. If they wanted the area between 0 and 9, you would add these three together. If they wanted 3 to 9, you would add these two. No, this one, because it's an acceleration time graph, that area is actually your velocity. So if you wanted to find the acceleration or the displacement on the acceleration time graph, what you'd have to do is you'd have to find, basically, you'd have to use one of those formulas. So you'd have to use like VFY VIY plus AT, something like that. You'd have to use one of those formulas. For example, on the lab, the second half is an acceleration, and so when it asks to find the displacement on those, some students are just doing V equals D over T and solving for D. Well, because your velocity is always changing because you have acceleration, this formula can't be used unless it's a constant velocity. So your acceleration is 0. So they actually need to use a different formula, to get that displacement, if that makes sense. So and that's about what they ask you to do for these graphs. There's one or two of them on the test that's like a short answer question, and you have to calculate the area under the curve and that kind of thing. So and that's how you solve it. That's how you do that. And so yeah, that's for that 1D motion test. You'll have I don't remember which graph it is. I know it's not a position time graph because those are too easy. But it's either a velocity time graph or an acceleration time graph, and you have to calculate the area under the curve. So I was just saying that these graphs plus the review I did last Tuesday are a really good way to review for that test that you guys have due tomorrow. Because last week we went over like frame of reference and displacement versus distance, and like how to calculate velocity and how to calculate acceleration. But we didn't go over the graphs because we hadn't gotten to that yet. So with the graphs and that and last week's, that should be a really, really good review for the test. But where can you find the link to last week's review? If you go to the on the home page, if you go to the right, you know how there's like all those little like kind of widgets on the side. If you scroll down to the user link section, it has a link to each review or each week, and so it should say like I think it says like velocity and acceleration review, and then it has like the date, and it'll go to a YouTube video